Hello everyone and welcome to the webinar. I will begin here by giving the microphone to Professor Jean Rasmussen from Aalborg University.
Thank you very much, Morten. So my name is Jean Rasmussen, and I'd like to welcome everybody to this webcast. I'm the handsome guy over there on the left-hand side of the screen. I'm probably trying to explain something very simple in a complicated way to my students. The guy on the right-hand side, his name is Kasper Pihl Rasmussen, who graduated just a couple of days ago, and he has been responsible for doing some of the work that we will be presenting in this webcast. Despite the similarity of names, we are not actually related. Rasmussen is a very common name in Denmark. So thank you very much for showing up for this event. And just a bit of housekeeping. You should have available on your screen a control panel, which you can expand or collapse as you like. If you don't need it, it's probably better to collapse it because then you can see the entire screen. However, one of the nice things about this control panel is that you can ask questions. And the nice thing about a webinar is that you can ask questions anytime that you like. So whenever there's a question that you want to ask, just type it into the question panel and submit it. We have a couple of guys sitting here. Morten, you heard him talk just a moment ago, and we also have Moon Ki-jung. And they are here to answer some of your questions. If they can answer the questions on the fly, then they're going to do that right away in the chat window. But otherwise, they might also postpone the question until the end of the webinar, and then I will answer the question orally. So please don't hold back if you want to ask a question. The agenda, we're going to talk about modeling of population ergonomics with AnyBody. And there are three parts to this, which will eventually take us to the animation that you see here on the right-hand side of the screen. But before I explain to you what that is, I have to take you through a couple of other issues, meant to explain what this is actually all about. And so I'll talk first about what it is that we want to do in a more general context. And then I'll talk a little bit more specifically about how to model populations. And then we'll get to the example, which is about car interior design. This next slide is a closer look at inverse dynamics. So some of you might know that inverse dynamics is what we actually do in AnyBody. And the model that you see here is a simulation which his name is Quang Wei Lin, and he's actually working in sports biomechanics, and he was interested in figuring out the effects of taping on knee injuries. So the model that you see here is a model of a subject who is jumping between two force platforms on one leg, and there has been a motion capture system working so that we have recorded the motion with those little optical markers that you could see as red and blue dots. And then you can also see the blue arrow. This signifies the ground reaction force, which was recorded with the force platforms. So this is the typical kind of model that we have been doing in the past, which we're also doing a lot still. What you can say about this model is that it's very detailed, but it's also what we can say it's retrospective. And the reason why it's retrospective is because we are modeling an experiment that happened sometime in the past. So we have to do the experiment first, and then we get all of the input for the model, and then subsequently we can investigate what happens in the model. So this is retrospective analysis, and that's not what we're going to talk about today. So this slide is really about what the webcast is not about. Instead, we're going to do something different. We're going to try to see if we can come up with a way of modeling things that might be happening in the future. So this is prospective analysis, and we've been working on this for quite some time. Actually, there was a paper out from my group actually many years ago in a conference in the European Society of Biomechanics, I think, where we modeled pedaling, and we actually also modeled we had a very simple model of a squat jump that we tried to predict. Recently, I had a PhD student. His name was Saeed Dawoodabadi Farahani, and he has been elaborating a lot on this. And so the two models that you see here are just like any other AnyBody model. You can see they are models with muscles, and they have a lot of muscles, and they have very detailed anatomy in every way. And these models are jumping, so they're performing a squat jump with or without arm swing. The nice thing about these models is that the squat jump they are performing is actually not a recorded squat jump, so there's no experimental input here. Instead, the result of the resulting jump here comes from an optimization process. So Saeed has been running an optimization, the purpose of which is to make the best possible squat jump within the anatomical limitations that the model has in terms of muscle strength and so on, degrees of freedom and what have we. And this actually works really well. It predicts squat jumps that are very, very close to what a real person would do. The only trouble with this is that the computation times are quite long, and it's also rather difficult to define the problem. So you can say this is like the $1 million solution with all the bells and whistles, but it might not be that useful for many practical purposes because it simply takes too long. So the question is, can we do something different? And I will this something different I will introduce to you in the words of a famous Swiss-French philosopher. His name is Jean-Jacques Rousseau, and you might recognize the first part of a famous quote by him, starting by "Man is born free," and we illustrate that with this model on the left here. This is the usual AnyBody model. This is just the standing model from the repository, and if you load this into the model, you can make it do pretty much anything that a standing model can do. So you have all of the degrees of freedom available and any possible motion this model could do, which is nice, but which is also a problem because you probably don't want the model to do any possible motion. You want it to do some particular motion. And so how can we get it to do that without actually recording the motion first? Well, that's where Jean-Jacques Rousseau comes in, because he starts his quote by saying man is born free, but then he continues, and everywhere he is in chains. Meaning that we might think that we are free, but actually everywhere we go, we are limited by a lot of different constraints. And this is actually completely true also for the biomechanics of our bodies, because of course we are limited by the strength, things that we can do. For instance, I cannot fly, and so we have certain limitations to us. But we also have some that are simpler than that. And I try to illustrate them with this picture of a person getting out of a vehicle. This is actually an old model that we used for many years for demonstration. But if you notice those different legends that I put on it, you can see that this guy getting out of the vehicle actually has to adhere to a lot of different constraints. For instance, he cannot, or he should try to avoid colliding with the door frame because he might hit himself, and anyway the door frame is not going to move. On the other hand, he might have the possibility to support himself on the door frame, so he can also put his hand there, and then the door frame will restrain the movement of his hand. Obviously, and also his joints have limits to their range of motion, so he cannot perform any motion. He has to work within those limitations, and then figure out how can I get out of the vehicle in those limitations. Now, if you try to park in front of a supermarket in a very narrow parking space, and you can almost not open the door, then you know that you actually have very limited possibilities of getting out of the vehicle. Now, the idea here is that if we can find a way of modeling all of those limitations, then they're going to take away much of the degree of freedom that the model has, and then maybe within this much smaller space, we can easier model the motion that we are looking for. So here's an example of that, where we tried doing this dynamically. So you see, this is also kind of from automotive engineering, because this is a person closing the tailgate of a station wagon. And the interesting thing about this is that it's pretty much just a standing model that I showed you before. And we have equipped the standing model with some constraints. One constraint is that the standing model has to remain in balance. Other constraints are, of course, the joint constraints, and another one is that the hand has to touch the tailgate. And so when the tailgate goes down, you can see that in order to continue touching the tailgate, that would mean that the person has to bend forward and extend the elbow somewhat, and maybe also bend the knees somewhat. So this model is trying to cope with all of those different constraints. The way we are doing this is by over-determinate kinematics, and that's actually a facility that has been available in the AnyBody modeling system for quite a while. It was developed by Michael Skipper Anderson, who is now my colleague at the university, but he used to be my PhD student, and as a part of his PhD work, he was developing this over-determinate kinematics. And it was actually developed for motion capture mainly. The problem with motion capture is that you typically have more markers than you have degrees of freedom in the model, and so you cannot let all of the markers drive at the same time, basically. So you have to find a compromise between all of the information you get from the markers, because you get an over-determinate problem. Now we're using the same kind of mathematics here in order to predict motion in this model. And the way this is done is that we, instead of using motion capture markers, we're simply formulating all of those constraints regardless of the fact that they might actually be mutually conflicting. But then this over-determinate kinematics will find the best compromise between those different constraints, and I'll get a little bit more into how we do that. So we call these models activity of daily living, and we haven't actually made very many of them yet, but it's something that we plan on doing a lot more in the near future. And so if we take again the words of Jean-Jacques Rousseau, then you see over here the idea. So we have first, man is born free. He has all of his degrees of freedom available. But then we formulate all of the constraints that he has, and these are the chains that Jean-Jacques Rousseau is talking about. And when we subtract those, there's just a little bit of freedom remaining. And after this little bit of freedom remaining, we still have to deal with that. And what we do here is we define some reasonable kinematic assumptions about what the person might want to do with those degrees of freedom. And then we have actually set up a problem where the system has the opportunity to find a compromise between all of those constraints, and that will give us a predicted motion. But notice that there are different types of constraints that we have to adhere to here. There are some hard constraints, like the guy has to keep the balance. That's not an easy constraint, but it's something we've been able to do in AnyBody for a while, actually. It's kind of special, but we can do that. It's no problem to do that in AnyBody. We have there's a hard constraint by the fact that his hand has to touch the door handle, and also the feet have to be on the floor. Those of you who were observing this closely saw maybe that the feet was sliding on the floor. Of course, that's not a good idea, so there's something there that we need to define a little bit better, but that would just be another hard constraint. Also, there might be some collisions defined here. So actually, in the motion that I showed you before, it wasn't really an issue, but if we let the guy stand closer to the door, then he has to avoid collision with the door. And those types of collision constraints, they're what the multi-body people are calling territorial constraints. So those are constraints on the space that you can occupy, and they're also related to, for instance, a guy getting out of the car that we saw before, and he was not supposed to collide with the door frame. Those are typically territorial constraints. There might also be range of motion constraints on the joints, so that the knees don't bend the wrong way, for instance. So all of those very different types of constraints, we have to be able to formulate them in the system, and I'm going to show you just a little more in a little more detail how we do that. And I have one equation in the presentation. That's the one that you get here, and I promise there won't be any others. This is actually from Michael Skipper Anderson's paper, and what I just want to show you here is that we have these are the way that the constraint functions are defined in his method for handling over-determinate kinematics. So psi is a constraint function. This is the specification that something has to be somewhere in space, And actually this, if this is fulfilled, then psi here should be 0. And you see psi is also over here, so we actually have psi times psi, so this becomes a quadratic term. And then we have in the middle, we have a weight function, WT. And this weight function, we can design that. We can determine what it should look like. Now, if we make W a constant, then we get a pure quadratic form. And the way the constraints will behave is like we see here on these graphs. They will look like parabolas. So if we have a constraint violation going out of this axis, then what will happen up here is that we get a penalization, and this penalization will work like a parabola. If W is a small number, then we get this shallow parabola at the bottom, and if W is a larger number, then we get the more steep parabola here. So we can assign different weights to these constraints depending on how important we think that they are. However, we can do much more with these constraints. We can actually not just use parabolas, because as I said before, W here doesn't have to be a constant. It can be a function. And we can determine what kind of function it should be. And so if we come up with a different way of defining W, then we can get the constraint to behave like this. And this is a territorial constraint, because you see this constraint is completely flat for a while. And then after this flat part, it rises very steeply. So what this does is that it says as long as you stay, as this particular constraint stays within this region down here, then I don't care. It can be anything. But don't ever cross the limit here. Don't go beyond the limit that I have defined, because then I'm going to penalize you very hardly. And of course, this flat region down here can be a territory that you're allowed to occupy, so a territorial constraint, or it could be the range of motion of a joint. And that's actually how we define these additional constraints that are necessary to make all of this work. So for the purpose of going forward, please remember this idea, and then I'll explain you something different in the meantime. Okay, so that was the first part. So that was putting prospective modeling into perspective, if you want. The next thing I want to talk about is population modeling, because what we want to do here is not only model the future, but we want to model the future not for a particular individual, but for a population. And so if you have this diagram here that might represent the different types of analysis that you could do with AnyBody, then we're over here on the right-hand side. We're going to do ergonomic product design, but we're not going to do it for a particular person. We're going to try to do it for a population of persons or people. And then we're going to try to do it for the overall body. So that's basically the domain that we are working in here. And the kinds of products that we are addressing are shown on this slide here. And there are, you can see there are like some products over here on the left-hand side and other products on the right-hand side. And I put them down on the slide like that because they are two different classes of products. The ones over here on the left-hand side, they don't really have any ergonomic adjustments. That means that once you buy these products, they are what they are. I mean, they don't change. There's no adjustment capabilities in these products. I know you can probably set up the cell phone electronically in different ways, but you cannot change the shape of the cell phone. So the musculoskeletal ergonomics is not going to change for the cell phone after you buy it. On the other hand, the products over on the right-hand side, those are products that after you buy them, they still have minor adjustments that you can use. So on the bicycle down below, of course, you can adjust the saddle, or you can adjust the handlebar, and it might even have different gears. So you can shift gears on the fly as you're riding the bicycle. The car at the top obviously also has adjustments. So cars are very expensive in Denmark, so most families only have one car, and that means that my wife and I are sharing the same car. I'm like a lot taller than she is, and so we wouldn't be able to share the car if the seat could not move back and forward. And so there are minor adjustments to these products, and those are the ones we're going to look into, because when we are designing ergonomic products for populations, and these products have adjustments, then it becomes very interesting for the designer to know how would the adjustments influence the comfort of or discomfort of the population, and how should we design the adjustments so that they fit the population as well as possible. So we need to get some data, some anthropometric data for the population in question. And there are many sources of anthropometric data, but unfortunately none is ideal. And I put down some of the possible sources that you can find on the internet here. There are some American sources and some European sources and some Japanese sources and so on. And they all have good and less good things about them. You can notice that I put down the year of these different databases. And if we take the one at the top, the ANSWER database, this is for American servicemen and women, and this is from 1988. So this is actually quite old now. So what can we get out of these databases? Well, generally, if you go and look at them, they have different graphical representations, of course, but what you generally can get is a number of dimensions for the human body. Like in this picture, we have the shoulder breadth from the ANSWER database, and they have measured the shoulder breadth of a whole lot of people. And it usually turns out that these data are normally distributed. So when we draw histograms, we can kind of make a plausible bell curve through the data, like what you see here. And this, of course, means that you can describe the data by means of a mean and a standard deviation. And most of the databases are providing just that. They have different dimensions that they have measured, but they usually report these dimensions in terms of the mean and the standard deviation. The problem with that is that you get the information from these sources or these different dimensions. You get them in such a way that they're independent of each other. So for each parameter you get the mean and the standard deviation, but you don't get the correlations between them. And I just want to show you what problems that can cause. So I took out of the ANSWER database. Now the ANSWER database is nice because the ANSWER database actually provides not only what you saw on the previous slide, but it also provides the raw data. And if I take 2 columns of the raw data in the ANSWER database, I have taken here the stature, so that's the height of a person, and then I've taken the parameter called the butt height. It's actually what they call it in the database. And obviously, tall people tend to have high butts, if you will excuse my language. And of course, these parameters are correlated. So if we plot them against each other, we get something like this, and you can see that these data are not independent. So let's see what would happen if we started modeling this independently. So that would mean that there would be a mean for the stature, symbolized by this black line, and there would be a standard deviation that we could compute based on the data, and there would also be a mean for the butt height, and there would be a standard deviation for that. And with that, we could actually make our Gaussian bell curves, and we could make them for each of those 2 parameters individually. And then if we started randomly generating people within this data set based on these 2 independent bell curves, then of course some of the people that we would be getting would be inside that cloud of blue points, but there would also be some of them that would be outside the cloud of blue points. So for instance, the 2 red points that I have drawn here are entirely plausible if you model these 2 parameters independently of each other, but they are very, very improbable in terms of the population data. So you see, if you use these data independently, then you're not going to get a population that's actually, you're not going to generate models that are representative for your population. So that's basically a big problem with these anthropometric databases. And Kasper and I have not solved that problem. But other people have been looking at that before. And there are particularly two groups that I would like to mention. The one on the left here is a group from the University of Michigan and University of Pennsylvania, and this is Parkinson and Reed, and they have basically been doing principal component analysis of this data. This allows the principal component analysis allows us to make a coordinate transformation in the space of parameters in such a way that we find the principal directions in these data, and then we can actually subsequently generate populations by means and standard deviations of this transformed data set. That's a really good idea, but that's not what we have done. We have taken the other one over on the right-hand side. This is a Korean group by Jung et al. And what they have done is they have also analyzed the same data, and again, it's the answered data. And what they have done is they have worked out the internal correlations between the parameters, and then they came up with a hierarchical method of generating random people that fall within the recorded population data. The way they do it, so we're going to take this part here on the right-hand side, and the way that these guys do it is that they make this hierarchy that you can see here. This is actually from this is a picture from Kasper's thesis, which he made based on the work of Jung et al. And so they take stature as the seed. So they randomly generate a stature. Of course, we can do that for one parameter because we have the mean value and the standard deviation. And then all of the other parameters, they have certain correlations, and you see the numbers here. They're the correlation coefficients between those different parameters. And every time we have one parameter, we can go down the tree and we can generate the next parameter based on the first one, but with a random component, such that that we start out with the mean value given by the first one here, but then we put a random component on it, and that way we can actually randomly generate different people within the same population. So we can generate as many people as we like. This is a little easier to implement, so this is what Kasper did. And as a result of this, what he can actually do is he can retain in his method all of the internal dependencies, between arm length or butt height or stature and all of these dependencies from the answer database, the raw data of the answer database. But he can offset this with statures from a different population. So now he can take not an American serviceman population, but possibly a European population or a Japanese population or something else, and he can just use a stature of that, and then he can generate a plausible population based on the internal dependencies of the answer database. So that's basically what we have been doing. Now, how do we get that into AnyBody? Well, AnyBody has certain different ways built into the models that come with the system, have some ways that you can scale them. And one of the ways is illustrated by this figure, which is actually a figure that you can bring out. You can load this model into AnyBody, and you can get this figure out. And you see these are dimensions of the different body parts. And these are actually dimensions between bony landmarks. So the idea with this is that you can take a tape measure and you can measure somebody, and then you could type in these numbers, and then you get a model of that person. But unfortunately, these dimensions are not measured the same way that the dimensions are measured, for instance, in the answer database or any other anthropometric database that you can come up with. These other databases, they would have different ways of dimensioning people. And so what Kasper did was he implemented a new scaling method in AnyBody, which corresponds with the answer dimensions. So basically the same thing, he just altered this method here, and then he came up with a new method which then takes the answer input. And now he can then randomly generate n different models, and n can be a very, very large number, with a natural variation in anthropometrics that corresponding to a certain anthropometric database. And so that was the population statistics. So now at the end of this, before we go to the actual example, please remember the following take-home messages. The first one is that we can do posture prediction with redundant kinematics. The second one is that we need, in order to do this, we need to have territorial kinematic constraints. And we can do this by these tailor-made penalty functions, so that we can model, joint ranges of motion and stuff like that. And then finally, we have the ability to make population statistics so that we can randomly generate a very large population of models. So this takes us to the third part and last part of the webcast, which is actually the example. And so this example comes from a very small Danish electrical car producer that you probably don't know, but I encourage you to take a look at their homepage because they actually make really cool cars. They make these little electrical cars that you see here on the right-hand side, and they're kind of unconventional in their cabin layout. And they try to come up with this cabin layout by using one of the standard digital mannequins that you can get on the market, but they were not really successful. I'm not really sure why, but it might be because the layout of this car is really different from what a normal car looks like. For instance, it has a driver's seat in the middle, which is somewhat different from normal cars. And so I'm going to just going to tell you how this is going to work, and then I'll give the word afterwards to Kasper, and then he'll explain the results. So you see here on the right-hand side, you see let me see if I can get my mouse to come out there. On the right-hand side, you see the AnyBody model of this package design, and you can see that it's a little bit different from a normal car in the sense that the seat is actually just a shell. It's not a soft seat like it would be in a normal car. So the person doesn't actually sink into the seat, which simplifies the computation of the H point a whole lot. So we basically just put the H point at a specific point in the seat. Let me just say a little bit more about how the model is made, and please focus first on these dots out here on the left-hand side. You see they go from red to green. And the red dot here is the hard constraint, and the only hard constraint we have is the constraint for the H point in the seat. The next class of constraints are the orange ones. So those are soft constraints, but they are soft constraints that have a high weight to them. So that means that they are soft, but they are very important for the algorithm. The algorithm tries to honor these kinematic constraints if in any way it can. And those constraints, what they do is they keep the hand on the steering wheel and the foot on the pedal and the back against the backrest, and also the head at the safe distance from the headrest. So this is a safety feature, basically. It means that if I were to move the steering wheel very far forward or the seat very far backwards, then actually the hands can let go of the steering wheel and the feet can let go of the pedals, but they will try their best not to do so. So the next class of constraints, so those are the yellow ones that come out in the picture here. And those yellow constraints, they are actually what we call comfort angles. So you can find in the scientific literature, you can find people who have been doing ergonomic studies of what sitting angles, what sitting postures people prefer when they're sitting in driver environments. And what we've done is that we have imposed those joint angles on the different joints of the model, but we have imposed them as very soft constraints. That means that if nothing else determines what posture the subject should have, then the subject is going to try to sit in that comfortable posture. However, if this is in any way violating the desire to keep the hands on the steering wheel or the foot on the pedal or something like that, then those orange constraints are going to take preference. And then finally, we have the green ones. And the green ones are for the steering wheel and they are for the seat. And those are territorial constraints like I showed initially. So remember that the nature of these territorial constraints is such that the algorithm doesn't actually care what value the constraint has, as long as it is within the range of motion. And of course, if we look at the seat here, then the seat is placed on a rail and it can move back and forward, but it can only move within a certain range because the rail has a finite length. And the question now, of course, is what length should that be in order to accommodate the whole population, and also where in the car should the rail be located. So what Kasper has done is he has actually generated a statistical population, by the methods I showed you before, of 16,000 different models. And then automatically each of those models gets placed according to the soft and the hard constraints in the car. And the territorial constraints, the seat and the steering wheel, they're soft as long as they're within their ranges. So they attain whatever values are preferred in order to get as close as possible to the yellow constraints. So in order to sit as comfortably as possible within the constraints, the other constraints that we have. But remember, the territorial constraint becomes very hard when we reach the end of the motions. So we cannot violate the length of the rail. And then we try to assess the comfort in terms of the constraint violation, but Kasper is going to get into that later. So now I'm going to hand the microphone to Kasper, and then he will explain some of the results that we see here.
Hello. What you see here in this animation is an animation of the different sized people, and this particular example only has 10, includes only 10 subjects. And this is showing the variation in the body sizes and in the body composition. And as you can see, the steering wheel and the seat are not moving. And this is because all subjects preferred the seat in the backmost position and the steering wheel in the lowest position. But after the first result, the design layout was changed and the seat rail was moved 7 centimeters back. And this allowed most of the subjects to find their optimal seat position. As you can see, the seat is moving now. But the steering wheel was still preferred in the lowest position by all subjects. Now this is a histogram that shows the distribution of the seat position. And this shows that by moving the seat back, the seat rail back, all females were actually able to find their optimal seat position. And you can see only the top percentile of the males still had to use the backmost position. And this is a great way to see how well the population fits the proposed design. Now we might get the idea to assess the discomfort by plotting the violations of the soft yellow constraints from before, in this case as a function of the stature. But this seems still to require some work before it's reliable. The males tend to have less discomfort than the females, as you can see, but all this still needs further validation. Now, this graph breaks down the discomfort contributions to the different joints. And as you can see, obviously, most of the discomfort seems to come from the right knee. And this is both for males and females. And this seems right because of the increased flexion in the right knee caused by the pedal compared to the left side of the person. So yes, that was a quick view of the results, and I will now give the microphone back to John Rasmussen.
Thank you, Kasper. So Kasper has been doing this work as his master's thesis in the sports technology education, which is a very, I think, very nice education we have at Aalborg University that combines sports science with technology. And this means that these students become very qualified for tackling issues that deal with the interfaces between humans and different products and technology. So I just want to round this off, and just by recapitulating the methods that we have been proposing here. So the first thing is that we propose to use the redundant kinematics engine and specify constraints in a special way, and use this to predict reasonable postures and motions. Do we know whether these postures and motions are correct? No, we don't, because we haven't conducted any validation at all. On the other hand, we're not trying to model the posture or motion of any particular person, but we're trying to model the postures and motions of a cross-section of the population. And I think you can see that there are definitely some nice and plausible elements to the postures and motions that you have seen. It's not unlikely at all that people might move that way. We have used these special weight functions to model the territorial constraints and also the range of motion of the joints and collisions with the environment and so on. And then we have used population statistics to randomly generate n different models, where n in this case was 16,000. So it's actually quite a lot of models. I can tell you that it takes about a night on an ordinary PC to analyze all of these 16,000 people in the data set. So it's definitely within the computational capabilities of yeah, you could even parallelize this process if you want, and then speed it up. We need some raw data, some raw anthropometry data in order to generate the populations. In our case, we got them from ANSWER, and out of the databases we have been able to get our hands on, ANSWER still seems to be the only one where we can get the raw data. So those were the ones that we used. However, with this method by Jung et al., we have been able to augment this data with current data for the local population. Actually, I didn't mention that, but we actually used a database called people size, which is from the UK and which we have in paper format. And so this was actually a UK population that you saw seated in the car. All of this statistical stuff that we have used in order to do this is programmed in Python. And then this Python script is hooked up with AnyBody. AnyBody has this capability that it can work together with Python. I didn't go into all of the technical details of how to do that, and the reason why I didn't do that is that there will be a webcast on the 30th of June, where Morten Lund is going to show how to use this to make statistical variations. You could use this for a ton of different things, not only population ergonomics like this, but also for investigating the sensitivity of the model to different parameters, for instance, like different sizes of bones or different, maybe uncertain parameters in your data set. The sign-up is open for that, so if you go to AnyBody Technologies homepage, you can sign up for that. In terms of the results, it seems like we can investigate ergonomic design problems like car interior design with this, and we can get some nice results, like, for instance, the different consequences of placing the rail with different lengths and in different positions. This is a little bit like building your own digital mannequin in AnyBody, and of course it's different from the types of analysis that we normally promote, because those are what we normally do is very detailed models with lots of muscles and kinetics and so on, and this was a purely kinematic analysis using a model that doesn't have any muscles, but has this quite anatomically detailed bone configuration with all of the anatomical joints in the bones or between the bones. This also allows you to use the data of your choice for the population statistics, so you can use not any data where you can get mean values and standard deviations of the data. And again, so the upcoming webcast is on the 30th of June, and this is about automating calculation processes in AnyBody using Python, and Morten Lund is going to show you how to do that. Actually, there's more prospective modeling coming out of the research group that I'm managing, the AnyBody research group, and I have a very happy announcement. This is my colleague Michael Skipper Anderson. He was the guy who originally developed the redundant kinematics, and he has had a huge success recently in the funding game. Skipper has applied for a very, very prestigious Danish free research grant called Sapir Aude, and he was able to get that grant in competition with scientists from all other scientific branches he was able to convince the referees that he exactly should have this money for a project on predicting the outcome of total knee replacements. So, and this of course also is very much prospective analysis, because Skipper is going to try to do this before the operation takes place. And very, very exciting work that I think you will hear more about in the near future. So if you think that this is interesting and you're thinking, how can I get to do this how can I get to use this on my problem? And all of this Python stuff and all of the population statistics and all of those strange constraints and so on, weight functions, it all sounds very complicated. I might need a little bit of help. Well, help is available from Morten Lund's webcast. It's also available from AnyBody Technology, who is hosting this webcast. So they have consultants who know how to do this, and they will be happy to help you. I also want to announce that Kasper, who actually did this work, he graduated the day before yesterday, and he is now available on the job market, and he is willing to travel almost anywhere in the world. So if you want to do this and you need a qualified person, let me know and I'll put you in contact with Kasper. So with that, I just want to say thank you very much for joining the webcast.